Hi! We've seen that what a computer does is our own convention, and no convention is more special than any other one. Before finding the answer to the question, are you a robot, we need one more step. And you'll get to make an experiment and check it for yourself. Previously, we've seen that a logic gate can be interpreted in different ways. In this example, there are 8 different interpretations. Here's a way to classify them. This ambiguity applies to any computer. This is because Turing machines can simulate other Turing machines. A Turing machine simulates another one if you can pick some of its states and pretend that they are the states of the simulated Turing machine. Without secretly changing the interpretation of the bits and the logic gates, programmable computers would be impossible. We would have to buy a different computer for each program. And even so, they would have to be much larger than they currently are. We may think that a computer can have a mind, but computer science herself tells us that this alleged mind would depend on our own conventions. The conclusion of the first part was that either a computer can't have a mind of its own, or if it has a mind, it has at the same time all minds allowed by all possible conventions. This seems crazy, right? So let's do an experiment right now. The experiment involves the partition problem. The partition problem is the following. You have a pile of coins and you have to divide it into piles of equal value. For example, this is not a fair partition, but this partition is fair. I will show you an algorithm that verifies if a given partition is fair. We will run the algorithm to verify a single partition out of 2 to the power of n. For any other possible partition, we will obtain the result without calling the algorithm again, just by decrypting it from the final state obtained from verifying a single partition. Everybody can download the C++ file from GitHub, test it, and check the code. The algorithm is explained in this paper. To do the experiment, you can download the source code from this link. This will take you to the GitHub page. Then you click on the link partition CPP, and it will show you the source code. You can download it by clicking on the download button, and then you need to compile it. The easiest way to do the experiment is just to run the program and it will guide you. It will tell you that if you press I, you can input your own partition to verify it, and if you press A, it will test that indeed all 2 to the power of n partitions are verified at the same time when a single verification is done. If you press I, you can input your own partition as zeros and ones. The program will verify it in 2 ways, the direct way and by decrypting from the final state of the computation the result for your partition. If you press A, it will verify for the default partition, then it will verify for all other partitions, and it will check that indeed the result can be extracted from the result obtained by decrypting the default partition. It writes the result in a file named test_results.csv. If you open the CSV file with the spreadsheet program, you will see if the test was successful. The first column contains all the partitions. The second and the third columns contain the difference between what each of the 2 parts received according to the partition. The second column contains the difference obtained by decrypting the result from the result computed using the default partition. The third column contains the difference obtained by direct calculation with the same algorithm. The fourth column contains yes if the test succeeded for that partition and no otherwise. The fifth column contains yes if the partition turned out to be fair and no if it didn't. If you look into the code, you will see what it does. When the program starts, the first thing it does is try to read the list of numbers. If it doesn't find it, it creates a new file with these numbers. This is the list of numbers file. You can put your own numbers in the file listofnumber.txt. Then the program looks for a file containing the partition. If it doesn't find a file named partition.txt, it creates a new one, partition.txt. This is the file listofnumbers.txt. This is the file partition.txt. You can write your own partition in the file partition.txt as zeros and ones for each number in the list of numbers. This will be the default partition, the partition that the program verifies and from whose result it then decrypts the result for any other partition. Then the program asks you what to do and it does it. The math behind the algorithm is explained in my paper. Does a computer think if no one is around to see it? I chose the partition problem because it is the easiest NP-hard problem. It's an NP-hard problem because you can make a fast program that verifies if a single partition is fair, but any program that looks for a fair partition is slow, because it has to search through almost all of them. I didn't want to test the relativity of computation for a trivial problem, and this is why I chose an NP-hard problem. But since it's very difficult to decrypt the alternative computations for this experiment, I had to make an algorithm that makes this decryption easy and independent of the hardware or the compiler. Okay, suppose you're right and all possible conventions are equal. What if there is a way to pick only one of the alternative computations and consider it to be the only one that is sentient? We will see that there's no objective way to do this. But what if all the alternative computations can be sentient? What if a computer can have many minds of its own? You'll see that your own personal observations contradict the hypothesis that the alternative interpretations can be sentient, so your own consciousness is not reducible to a computation. But first we need to explore what alternative computations are possible. Since a computation can simulate another computation, a computation applying an algorithm to a particular input can simulate the application of the same algorithm, but for another input. But then, when can we reinterpret the computation for a particular input as the computation done with the same algorithm but for another input? You can take a break to think about how to answer it. The computation for a particular input can be reinterpreted as the computation for another input if all the states of the computer corresponding to each step in the two computations are different. Right, this condition is ensured automatically if the program doesn't erase the input data and if the computer counts the steps or keeps the time. Then the causal relations between the computer states correspond at once to the computation steps for the first input and to those for the second input. We can think of this as equivalent to resetting the computer to the initial state for the first input, replacing the input, and then computing the result for the second input. Except that we don't do this, we just decrypt the second result from the first result. Here are some paradoxes based on this experiment. The all-at-once paradox. Install the partition program on a server. Allow clients to call the program by sending their own input data. They can encrypt the input data before sending it to the server. The server sends the final state of the computation back to the client. The client can decrypt it, finding the desired output, just like in our experiment. The server collects the requests from the clients and groups them by the input which may result from encryption. Then it runs the program for an input and sends the final state to the clients who send that input. One day, 2 to the power of n clients sent the same input, but before encryption, each of them had a different input. So the server computed all 2 to the power of n requests at once in a single physical process. The all-at-once paradox, the AI version. What if we do the same experiment again, but with an AI on the server? The AI collects the requests and runs the partition program in debug mode step by step. When the AI encounters a number, it may trigger some association. For example, encountering the number 7 makes the AI think of Snow White or sunrise or days in a week. After more free associations, the train of thoughts of the AI may diverge arbitrarily. Suppose each client receives not just the result of the partition program, but the final state of the server, including the AI. Then, by applying a very complex decryption and using a much more powerful computer, each client would decrypt a different version of the AI from the final state of the same computation. These versions of the AI will be very different because they made very different free associations. And yet the server runs all of them at once during the same physical process. The rewriting the history paradox. An AI is trained with certain input data. From the final state, we decrypt the alternative results corresponding to different input data. To the user, it would appear as if the history of the AI was erased and replaced with a different one. For example, if the AI was trained as if the world's history is the history of our world, the decryption can find an AI remembering the history of the Harry Potter universe, or of the Star Trek universe, or of the Star Wars universe, depending on how the client decrypted the result. The multiversal Turing machine paradox. For a programmable computer, programs are just a special kind of input data. So by reinterpreting those input data, a program can be reinterpreted as other programs. Then a computer with unlimited memory could run all possible programs at once, a multiversal computer. So if you run an AI, you run simultaneously myriad versions of the AI. One version for each possible training data. They can have completely different worldviews, but they can't communicate with each other. The AI is ambiguous and observer-dependent, so it can think unambiguously even about a number. Now back to the first question. There are many alternative AIs at once on the same computer. Maybe there is a method to decide that only one of the alternative computations can qualify as being sentient, but such a criterion should not depend on new data the AI receives. The data can be reinterpreted in myriad ways. All of these alternative interpretations of the AI will therefore satisfy the same criterion. It's either all or none. Either none of the incredibly many interpretations of the computation that we call AI can be sentient, or all of them are. But isn't your argument just like the triviality arguments? Let's recall the triviality argument. According to Putnam, we have a rock whose temperature increases continuously in a time interval. Then, successive states of this rock can represent the steps of a computation, and in fact of any computation. This is considered by some to prove that nearly anything can compute anything. It was objective by others that to be a computing machine, the rock has to be able to represent computations for all possible input data. But this can be fixed by adding a dial to represent all possible input data, as suggested by David Chalmers. In fact, the rock itself can be the dial. By rotating it before the heating interval begins, we can encode different inputs in its orientation, so we can distinguish as many different computations as needed. The rock can be oriented in an infinite number of possible ways, so its possible orientations can encode an unlimited number of possible input data. So then, to reject this updated version of the triviality argument, it was proposed that the structure of the machine implementing the computation has to be the same as the structure of the data it represents. But this is not what computer science says, neither in theory nor in practice, because it contradicts Turing universality and programmable computers. And this is not how we use computers, how we develop them, how we program them, and so on, because this is done according to computer science. We've already seen in the first episode that if the only data that can be encoded in a computer are those with the same structure as the physical structure of the computer, there will be no universal computers. So our analysis of computer science, proved by the crazy partition experiment, vindicates the triviality arguments. As for the second question, but what if a computer can have, instead of a mind of its own, many minds of its own? What's the big deal? Next, you'll see that this would contradict your own personal observations, so your own consciousness is not reducible to a computation. See you soon!